Hello! First period honors algebra students, Mr. Lawrence. Not really here, but I will be in later today, and there is a help session after school today, hopefully to see some of you in. Hey, we're going to pick up that section that we skipped on scatter plots and lines of best fit. And I know some of you went and kind of taught it to yourself anyway, because one of the homework questions asked about it, which was awesome of you to do. But we're going to go over things here. So let's talk about, first of all, making a scatter plot and describing its correlation. So let me get this open here. I'm just working from digits, so you could always go back and check that. Okay, you could go back and rewatch this on your own. All right, so first of all, they give us a graph, and they're showing the altitude in meters and the temperature in degrees Fahrenheit. Now, I don't know if you realize this, but generally speaking, the higher altitude you're at, the colder the temperature. Now, you don't notice that if you just go to the top of your roof, but if you go up to 1,000 meters up, you might start to notice. So we have this input-output table, all right? And they want us, I believe, first of all, to make a scatter plot of the data, all right? And so they're going to set up a graph here, and you can go ahead and do that with us if you want to do just a little sketch graph in your notes. Doesn't have to be on graph paper per se. So it says the highest altitude is 5,000 meters. A reasonable scale on the altitude axis, or in this case the x-axis, is from 0 to 5,500 with every 1,000 meters labeled. Okay? And then they're going to set up the y-axis. Okay. Well, and the temperatures looks like they're going to about 60, a little bit above. And so they're counting by 10 degrees, right? Because they're skipping one every 20. Okay. And so now they're going to plot these points as best they can. Now, of course, they won't hit exactly on the nose, but they'll do the best they can. And you see that the points are being plotted. Okay. Now, what do you notice about these points? I mean, certainly they're not linear, but they do follow a trend, right? And we notice this trend is kind of like a line. And so what we can do is we can just determine a relationship. We notice that, generally speaking, the higher the altitude, the colder the temperature, right? Okay, so let's see here if that's what they came up with. Yeah, the temperature outside the plane tends to decrease as the altitude of the plane increases. So the data is said to have a negative correlation. Now you've got to be careful with the word correlation. Correlation does not guarantee causation. For an example, do you know that as more ice cream is eaten, more murders are committed in the United States? Yeah, it's true. Okay. Now, some of you just heard that I said eating ice cream causes murder. I said no such thing. I said when more ice cream is eaten, more murders are committed. Eating the ice cream does not cause murder. There must be something else driving both factors. Well, let's think about it for a second. When do you tend to eat more ice cream? Well, some of you say when you're depressed. Well, maybe so. If you eat for comfort, then that could be true. But don't you tend to eat more ice cream when it's hot out? And when it's hot out, don't people tend to become more irritable, less patient because they're uncomfortable with the excessive heat? And therefore they lose their temper a little more quickly? And so what happens is you have this outside thing that we're not talking about causing more ice cream to be eaten and also causing more murders to take place. Another ridiculous example is that there is a correlation, not causation, a correlation in the 1970s between the number of storks in Seattle, Washington, and the number of babies born. And of course that's funny because, the old myth about storks bring babies, I don't know, your parents probably don't tell you that. They don't tell kids those kind of things anymore. But it's kind of funny. Now, again, It is not causation. The storks were not bringing the babies, right? What you had going on in the country in the 70s was an economic downturn, a recession, if you will. But in Seattle, Washington, they were experiencing a boom due to technology. You know what? This might not have been the 70s. This might have been the 80s. I can't remember. Anyway, so what happened was the economic boom was attracting the type of people that go into technology. Well, they tend to be young people who just graduated from college, etc. They're hip with the new technologies. Just watch your parents, working some of the technologies that you think are so simple. Don't worry, it'll happen to you too. Your kids will do technology way better than you ever could, and you'll be amazed at oh my gosh, how do they stay up on all this? And it'll just be natural for them. They're just growing up with it. So anyway, young people were being attracted to Seattle, Washington for jobs in technology. We're talking 22, 23, 25-year-olds, and they were meeting other people their age and getting married and having babies. Well, there's two things that humans are guaranteed to produce. You put enough humans together, you will get these two things. One is babies, and two is garbage. And so what happened was these young professionals were getting married, having babies, producing more garbage. The garbage got put in the landfills. Storks are scavengers and like to go through garbage and eat it. So the abundant food supply was attracting more storks. Hence, you had an increase. But the one did not cause the other. They were both caused by one was caused by the economic boom, and that brought more people, and more people produced garbage, and the garbage produced the storks. The babies did not produce the storks didn't bring the babies, okay? So you've got to be careful with correlation and causation. All right, so this is a negative correlation because if you drew a line or found the trend, it would have a negative slope. That's a negative correlation. And again, it does not mean causation. Be careful with that. Okay, here's another example. It says, make a scatter plot of the data in the table below. What type of relationship does the scatter plot show? I'd like you to pause the video and make your own little scatter plot. Write in your notes, doesn't have to be on graph paper, and see if you can determine what type of relationship it shows. Okay? All right, if you're still watching, I assume you've tried this. Let's see what they say. There's their little scatter plot, and if you look, let's see here, it looks like it's trending upward. It's almost perfectly linear, and so I would say as more dollars are spent, more gallons are purchased, okay? Or as more gallons are purchased, more dollars are spent, all right? So it's got a positive correlation, okay? And again, that doesn't guarantee causation, although in this case, it kind of looks like it could. All right, now, writing the equation of a trend line. A trend line. In this problem, hold on, I can't seem to stop it. Quit talking. Make a scatter plot of the. Okay, so we're going to make a scatter plot of the data, and here we go. These are graphing the points. Okay, and there we go. Now, you've got to be able to draw an effective trend line. All right. Well, an effective trend line is an accurate trend line should fit the data closely. In other words, follow the path of the points. There should be about the same number of points above the line as below it. So when they lay down their ruler and they draw their line, watch this, there it goes. Okay, it looks like 1, 2, 3, 4, 5 are exactly on the line. There's one below, one above, one below. Okay, that's the best they could do. They tried to split it evenly. It's pretty close. Now, data this tight, this close to the line, the correlation is going to be very strong. It's going to be close to +1. In other words, the slope of this line is going to be close to 1. All right. If you had plots kind of all over the place, points all over the place, then it wouldn't be as strong, okay? And we'll look at some of that a little bit. All right, so let's see here. So they found 2 points, and they're going to calculate the slope of the line. You know how to do this. You know, you get m, right? And so here they go. Now let's see, what do they come up with for their slope? Well, they get 5 2/10, right? Okay. I think I just contradicted myself. I said the slope was going to be 1, and I think I made a mistake there. Apologize for that. Anyway, so I know why it's not 1, because the scales are different on the x and y axis. My apologies. All right, so now they're going to use point slope form to help them write the equation of the line, right? Using point slope form. And then they are going to convert it to slope intercept form. And there they go, okay? Now, they want to estimate the weight of a 7-month-old panda. And since we're talking months for our independent variable, all they have to do is put 7 in for x and do their math, and there we go. A panda is about 32 7/10 pounds. Okay, you look over here, and they're going to 7 months old. Okay, so there you go, 7 months, and look, they're over there. Now let's see, they're counting by sixes, so this would be 30. That's 36. Midway in between 30 and 36 would be 33. And so this is going to be 32 something. And so it's a pretty good estimate. See that? Based on that trend line. Now it's not perfect because it's only a trend line. And notice the approximately equal to 32 7/10. All right. So this one says, all right, make a scatter plot of the data, draw a trend line, write its equation. What is the approximate length of a 7-month-old panda? Okay, you go ahead and do that. When you're ready, unpause the video. Okay, here comes the solution. So there's their trend line, and there's their scatter plot. And you look, you see some are off a little bit, but they did the best they could to follow the path of the points. Looks like they've got more points below the line than above, but it's close. And then they came up with an equation of y equals 2 2/10 x plus 8 9/10, and the estimation is 24 3 inches. Now, if you do this on your own, you're likely to get a slightly different equation. Okay, it may not be exactly 2 2/10 because your scatter plot is going to look a little bit different. Okay, so let's talk about identifying whether relationships are causal. All right, so in the following situations, is there likely to be a correlation? If so, does the correlation reflect a causal relationship? And explain. So let's see, what's the first example here? The number of loaves of bread baked and the amount of flour used. Okay, so as more and more loaves of bread are baked, do you suppose that more and more flour has to be used? Of course, right? So there is a strong correlation between the two. Now, does baking bread cause the use of flour? Absolutely, because you can't bake the bread without putting flour in. So that is a correlation and an example of causation. Okay. All right, let's see the next. Positive correlation, also a causal relationship. All right, now here's another example. The number of mailboxes and the number of firefighters in a city. Well, let's think about it. If there's lots of mailboxes, is it likely that there's going to be lots of firefighters? Well, the more mailboxes there are would seem to indicate that it's a bigger city. A bigger city is going to need more firefighters, right? So this has a positive correlation. Now, is it causal? Well, what drives the need for more mailboxes? People moving into homes or apartments or whatever. If I live in a city, I'm the mayor of a city, let's say, and I see a big open field, and I decide to put up 15,000 new mailboxes. Don't assign them to anybody. Just put up 15,000 new mailboxes. Will the number of firefighters increase? Of course not. That's ridiculous. So this is a positive correlation, but it is not a causal relationship. All right, let's look at another one here. Is there likely to be a correlation between the cost of a family's vacation and the size of their house? If so, does the correlation reflect a causal relationship? Well, let's see. If you take expensive vacations, you probably have more money. And then does it become more likely that you have a bigger house? It's possible. I would say generally that's probably a true statement, right? Generally speaking. So if you spend more on the vacation, you tend to have a bigger house, okay? For example, a family without a lot of money, they will stay at bargain hotels or roadside hotels. Somebody with a lot of money might be staying at really fancy hotels like the Ritz, okay, things like that. Somebody might be taking a vacation to Columbus from Brunswick, and somebody else might be taking a vacation to, say, Argentina, which would certainly cost more if they have more money. So I would say there is definitely a correlation, not guaranteed, but correlation. But does the cost of the vacation guarantee a bigger house? Does it affect it? Like, maybe a couple is saved up, and for their 20th wedding anniversary, they decide that they're going to do something very special, and they take a big extravagant vacation. They go on a 3-week tour of Europe and the Middle East. Does that mean when they come home they're going to have a bigger house because they spent more money on their vacation? No, absolutely not. Having a more expensive vacation does not cause a bigger home. Okay? All right. I'm going to wrap up this video now. You go ahead and work on the assignment. It's 5-7, I think. But it is not homework. You work on it in class, and when the bell rings, that's it. You don't have to worry about it right now. We'll pick it up later on. For homework, I want you to be working on studying for your midterm. Remember, it's only a week from Monday. Okay, I will be in at 5th period, and so make sure that you are planning on coming in for help after school. I'm going to be here. All right, that's it. Mr. Lawrence signing off. Have a good day, everybody.